In this video, we will examine how neural networks function. The idea behind neural networks is that they function similar to how our brain works. Our brain is composed of cells known as neurons. For a very simplified description, a neuron is composed of a nucleus, dendrites, and axon. Dendrites are essentially sensors and receive signals from neighboring neurons. These signals, which are sent towards the nucleus, can be either excitation signals or inhibitory signals. There can be many dendrites and thus many exciting and inhibiting signals being sent towards the nucleus at the same time. Depending on the number of exciting and inhibiting signals, the neuron cell may generate its own impulse signal. This is known as the neuron firing. If this occurs, this signal is transmitted via the axon branch of the cell towards other neurons. The complex arrangement of these neurons in our brains allows us to process data, control our bodily functions, and make decisions. Our artificial neuron, highlighted by the yellow box, tries to replicate its biological equivalent. In the case shown here, we have a very simple neuron with two inputs and one output, although note we could potentially have many more inputs and outputs. The neuron itself contains parameters labeled W and B, and in this case, is labeled with a step-shaped image at its center. What we do to process this incoming signal is take each input and multiply it by the weighting value W. These weighted signals are then added together, along with the bias term B. So in this case we have x1 times W1 plus x2 times W2 plus B. This summed value is then fed into our central function. In our image, this is a circle with a step shape. There are various forms this function can take, but its main purpose is to firstly limit the output and secondly to add nonlinearity into the calculation. Our step-shape function we are using in this case is called a hard limiter function. For this, if the input value is less than 0, the output is 0. If the input is greater than or equal to 0, the output is 1. The output of this function is the output of the neuron. The values of the weights and bias are critical for the neural network to function as intended. For simple cases such as the single neuron here, we can work this out mathematically. However, typically what we would do is train the neural network. In this process, the weights and bias values are adjusted through mathematical algorithms to obtain the desired solution. A lot of work by mathematicians and computer scientists have gone into developing these algorithms. For this module and for most people developing AI solutions, we do not need to know the details of how these algorithms work. We can use pre-written computer routines to do this for us. However, we do need to decide on the parameters to be used by these algorithms. We will discuss this in the next video. Let's see an example of how a neural network functions in practice. We will consider a very simple image recognition problem. Note that this is extremely simple but allows you to get an idea on how the mathematical processes are working inside the network. Our problem will consist of an image consisting of 2 pixels, and what we would like to do is recognize if a number 1 has been written. If you look at the 4 images, the first image is blank. The next 2 images are just a dot or point, and only the last image represents a line going down indicating the number 1. For this basic example, there are a total of only 4 input variations, and so we can map out all possible solutions. However, generally speaking, it will be practically impossible to map out all of the solutions. Typically, you would only be able to use a small percentage of the possible input variations. If we use this neural network configuration with these weights and bias values, we will get the desired result. So let us test this. If we have x1 equal to 0 and x2 equal to 0, we get 2 times 0 plus 2 times 0 minus 3, which is minus 3, so our hard limiter outputs 0, and so our neuron output is 0. Next, We will try x1 equal to 1 and x2 equal to 0. We get 2 times 1 plus 2 times 0 minus 3, which is minus 1, so our hard limiter outputs 0, and so our neuron output is 0. If we have x1 equal to 0 and x2 equal to 1, we get 2 times 0 plus 2 times 1 minus 3, which is minus 1, so our hard limiter outputs 0, and so our neuron output is 0. Finally, if we have x1 equal to 1 and x2 equal to 1, we get 2 times 1 plus 2 times 1 minus 3, which is 1, so our hard limiter outputs 1, and so our neuron output is 1. We have therefore satisfied the requirements of the problem. Some points to note in this example. Firstly, we have supplied the input and output. This is known as supervised training and is a common way to train neural networks. Secondly, in this case we have supplied all the input and output values possible, and so the network will always be 100% accurate. In practice, this will never be the case as datasets have too many input variations for us to consider. Remember that the real power of neural networks comes from being able to generalize. That is, you only need to give it a few examples, and it can then deduce what other input variations correspond to, although accuracy will never be 100% for these cases. As another example, let us consider this network which has 4 neurons. If we consider an input of x1 equals 1 and x2 equals 0, then the output from the first neuron is 1 times 1 minus 0.5, which is plus 0.5, so the output here is 1. For neuron 2, the input is x1, which is 1 times 1, plus x2, which is 0 times 1 minus 1.5. Thus this total is minus 0.5, so the output is 0. For neuron 3, the input is x2, which is 0 times 1 minus 0.5, which is minus 0.5, so the output is 0. For our final neuron, the 3 prior neurons had outputs of 1, 0, 0 respectively, so our input into this neuron is 1 times 1 plus 0 times minus 2 plus 0 times 1, which equals plus 1, so our final output is 1. At this point, pause the video and see if you can work out the output for the other combinations. Once you have completed the table, you should get this output mapping. In this case, the network has recognized that a dot was written. The solution to this recognize the dot problem has required a more complicated network. This increase in complexity can be explained if we consider the mapping of the inputs to the outputs. In the case of recognizing a 1, if we mapped out all possible solutions, we can easily separate the different possible outputs with a single straight line. This line is essentially what our first neural network example represents. For our recognize the dot problem, we cannot simply use a single straight line. To separate the possible outputs in this case, we have needed to use more neurons to define a boundary in our map between our two output states. You will have noticed that in our second example, we have an additional layer of neurons. In fact, we could potentially have many more additional layers. These are known as hidden layers and are located somewhere between the input layer and output layer. The user does not directly access these layers. Deep neural networks have many of these hidden layers. As mentioned in the first video of today, we could have simply used a few if statements to solve these example problems. The examples were actually just logic operators. However, the point of these examples was to show you how neural networks function. The next example will demonstrate why using if statements is not feasible. In the next video, we will look at a realistic image recognition example.